Jackie is a professor of materials physics at the University of Cambridge, where she leads a research group in molecular engineering. She's a leading materials physicist whose work sits at the interface of physics, chemistry, and data science. And her main scientific accomplishments are pioneering data-driven materials discovery. Jackie has been a prominent advocate of integrating artificial intelligence, machine learning, and data sciences with experimental and computational methods to create a design-to-device pipeline for discovering functional materials. Advances in optoelectronic and energy materials. Her research has significantly contributed to the design of organic and molecular materials for applications such as nonlinear optics, photovoltaics, and solar energy harvesting, including new light harvesting chemicals and smart solar technologies. And development of photocrystallography and diffraction methods. Jackie has made influential contribution to structure property relationships in materials, especially through X-ray and neutron diffraction and photocrystallography, enabling the study of light-induced structural changes in crystals and many more. Her research and leadership are collaborative, international, interdisciplinary, and innovative, as recognized by the Warren Diffraction Physics Award in 2021, by Royal Society Clifford Patterson Medal 2020, 1851 Royal Commission Design Fellowship in the term of 2015 to 2018, as far as I understood, Fulbright Award, also Royal Society University Research Fellowship, Royal Society of Chemistry, the school's Analyst Competition Silver Medal, Brian Mercer Feasibility Award, 18 Franco British Science Prize, Senior and Junior Research Fellowship from 1999 to 2009.
At the St. Catherine College, Cambridge, and the BCA Chemical Crystallography Prize in 2000. London Business School Diversity in Leadership Award 2021, London Business School Social Good Award 2023. Jackie also led an artificial intelligence for materials big project team of 89 collaborators that led to the entire team being awarded the Royal Society of Chemistry Materials Horizon Prize 2025. And for those who complain that science is difficult, I will dedicate this final fragments of Jackie's CV. Jackie holds a PhD in physics from the University of Cambridge and PhD and Bachelor of Science in Chemistry from the University of Durham, BSc in Mathematics, Diploma in Statistics, Diploma in Physics, Bachelor in Engineering from the Open University, an MBA from London Business School, and MSc in International Strategy and Diplomacy from the London School of Economics. Really extremely impressive, Jackie. Congratulations. Jackie, the screen is yours.
So thank you very much for the very kind introduction. The pressure's now really on to give a really good talk, right? But thank you, and it's really a delight to be part of this lecture series. So I do want to thank the organisers. It's really great to give this talk. My talk will be quite different to Benoit's. So I'm actually going to talk on more the experimental side of what I've been doing with the photocrystallography developments and the associated parts, although there is a sort of prospective quantum sensing application side, and that's what I will try and highlight through the examples that I provide. So hopefully if there's any sound problems, you'll hopefully scream at me now to tell me, otherwise I'm going to carry on hoping all is well. So thank you again for the invitation. So what I'm going to talk about is first of all the chemical background behind the problem, and I explain the chemical compounds that are involved in these quantum sensing actuators. And then I will tell you about how we do the experiments in a simple way to give you some idea of what happens in the lab. And then I will actually give you some examples of cases where we've discovered some single crystal optical switches and also single crystal optical actuators. And following those examples, we'll maybe have a look at how we can maybe tailor those towards real world applications, which is some way in the future, I should add. So let's begin with what are single crystal optical actuators, and that's harder to explain. It's easier to explain what are light-induced molecular switches, and so hopefully let's maybe look at the switches first before we talk about the slightly more advanced problem of actuators. So as many of you will know, a molecular switch, at least a light-induced molecular switch, is a case as a material where you shine light on it and then something in the molecule changes. It moves or switches in some way, and hopefully in a controllable way. And so this picture I'm showing is an example of the chemistry, which will be the focus of this discussion. So on the left of the screen, you will see the generic molecular or cationic formula of the complexes that we're going to be looking at. These are ruthenium-based coordination complexes, and the equatorial plane, they always contain NH3 groups, so tetraamine, so they will be constant throughout the presentation. But the photo action will be happening with the sulfur dioxide ligand, and I'll tell you a bit more about that in a moment. And then, so you will always see some photo action there, and then the trans ligand to the sulfur dioxide group is something we will change. This is X, so we will be changing ligands out at the X position because that influences, of course, with the trans influence, the SO2 photoactive site. And then the counter ion will mostly be a tosylate, but there's also an example of a chloride as well. So just so you know, there's some a counter ion which we'll call Y. Okay, so that's the generic complex, and it's quite important to remember that as we go through, but I'll give you many examples. And so in terms of the photo action, what is happening is that you have this sulfur dioxide ligand bound in the dark states between the sulfur and the ruthenium. But what happens when you cool these single crystals down? So this all happens in the single crystal state. Everything I'm showing you is in throughout the presentation will be in a single crystal. And when you apply green light generally and keep it cold, let's say 100 Kelvin, that type of cold, then you fire light at it and it will convert into one of these two photoisomers. So it goes from sulfur bound, you see on the right there, to there's either a side bound form here or actually the oxygen bound form here. And so there are potentially up to 2 photo-induced states that you could obtain. Of course, that's quite difficult to see in a single crystal when you model it. So you may see these overlapping in some sort of almost looking like a disorder type problem. But if you're lucky, you'll get a clean transition. And then you can reverse it by heating it up, right? So if these are photo-induced at about 100 Kelvin, then you can heat it up to get back to the dark state, for example. And what you see in terms of the physical manifestation of the crystal is generally that you'll have some photochromic effect. So the crystals will change color, particularly when you're going moving from the this dark state into the oxygen-bound ruthenium photo-induced state. So that's the nature of the system. So that's the switching part. And I'll go through now the sort of mechanism that we typically see in these this series of complexes. And as I say, where we change the trans ligand, so that's the ligand here. In this case, this is 3-chloropyridine, again, trans to the sulfur dioxide group, and this is all in an asymmetric unit. This is Y. Remember, there are counter ions, so this is the tosylate. There's 2 tosylate groups, and of course they're not doing much photo action, but actually they're important because, of course, everything's happening in the single crystal. So all of this is very much constrained in what they call a reaction cavity, because, of course, there's only so much volume around here, and depending on the counter ions, they can actually be quite important for more steric reasons. So this is an asymmetric unit of the 3-chloropyridine example where we're changing X. And when you cool down this particular complex to 100 Kelvin and you apply green light to it, so that's at about 520 nanometers, then you tend to get in this case, the oxygen-bound sulfur dioxide. So it went from sulfur-bound to oxygen-bound. And then what you see here, because of this reaction cavity, right? So if it goes to the oxygen-bound, that's quite a big change while keeping everything in the single crystal. And you see this, the other oxygen that's not bound is sticking out. And because it's now it's kind of in here near this counter ion, that becomes actually quite uncomfortably close for this counter ion, right? So that presents a very steric interaction. It's really quite small, and so in fact it's so small that what happens is, not for all of the molecules involved, or the ions, but for most of them, then the counter ion, the tosylate, actually rotates in terms of the arene ring. And what you can see here is then that the arene ring rotates sterically to alleviate that strain. So instead of 2.3 Armstrongs, the separation of the hydrogen and this oxygen, you're now just over 3 Armstrongs. So it's now a lot more comfortable. And in this particular case, there was some symmetry involved, as you can see from the suspicious 21 and 21% photo conversion. We managed to isolate this because 21% did rotate and then 21% didn't, out of the photo converted species, which was in total 42%, right? So 42% of the sulfur dioxide ligands actually photoconverted. The other amount stayed in the dark state. So that's one thing. And then of the 42% of oxygen-bound SO2 that formed, half of the arene rings rotated to alleviate that strain. So these are really quite complicated, disordered crystallography problems, really. But just to show you an idea of how complicated these things can get. And every time you change X, so this transligand, and Y, in this case, the tosylate groups, it's very hard to predict what will happen here, right? Because everything is really dependent on this reaction cavity, right? And it's very much about, exactly the shape and size of things that are happening. So it's quite hard to predict. But we'll go through some examples and see what happens. So that's really just to give you an example to introduce you to the type of chemistry that's happening. But most importantly, remember, it's all happening in the single crystal phase. So how do we even do these types of experiments? So in terms of the diffraction, we essentially use a technique that's become known as photocrystallography. In essence, what it is an in situ X-ray diffraction experiment where you shine light at the single crystal, and you know this, right? This is a crystallography apparatus, and first of all, in fact, before you shine light, you will do a standard crystallography experiment. So you obtain the crystal structure of the material in its dark state. And there it is. And then you will essentially do a second experiment while keeping the crystal on the diffractometer, keeping it cold. Then you apply light, and then you will maybe get, if you're lucky, a nice clean state. It doesn't always happen like that, of the light-induced species, right? So in this case, now it's the oxygen-bound SO2 ligand isomer. All right, and then heat it up, and you'll hopefully get back to the dark state. The techniques developed over the years. A guy called Philip Coppens from the US worked very hard on this. Unfortunately, he's passed away, and then I've been working with him and others along the way. So there's a few reviews there to help. So that's the nature of the crystallography, and this is what you tend to see in terms of what the crystal structures look like. And I've already hinted at this before, but this is the dark state, so that's quite easy to refine a structure. And the moment you see the light-induced state, because often you don't get full conversion of the sulfur dioxide, then you still see some of this dark state. And then you model it like a disorder problem. On top of the dark state, you model the light-induced species, right, which are really quite close. You know, so you have quite difficulty sometimes refining them because they're almost overlapping with some of the dark state and so on, right? And sometimes you can have one species formed, and sometimes even the side-bound form can also be overlapping with the oxygen-bound form, right? So these can be quite tricky to refine, but that's basically how we actually try to refine these species. So that's the diffraction side of things. But because of course we're firing light at the system, it's really to understand the chemistry and the physics of the problem. We really have to not only just do diffraction, but we also have to do optical spectroscopy and also microscopy, and as you'll see later, some other forms of microscopy, because we've really got to understand the light-induced part of the process as well as just the structure. Together with the photocrystallography, we do a lot of optical absorption spectroscopy, but importantly, not the typical optical absorption spectroscopy that happens in most labs. We're doing single crystal, low temperature optical absorption spectroscopy, which is essentially not a commercial apparatus to my knowledge, and we've had to build our own to get this to work. And likewise with Raman spectroscopy, I'm not showing any today actually, but in that case we actually use the light of the Raman spectroscopy to actually excite it, and then use temperature to play games to switch on and off the light induction so we can see the vibrational spectroscopy. And then I'll show you some examples of the microscopy, the optical microscopy that we run together with while we're actually monitoring the optical absorption. So just to give you an idea, we're really using multimodal methods experimentally together with the crystallography to understand the full both optical properties and also the diffraction. And this is just to give you an example, the experimental setup that I've made together with some colleagues at Argonne National Lab. And it's a sort of bespoke setup that every time I go over there, we have to make it again because it doesn't exist unless when I'm there. But this is an optical cryostat, a low temperature optical cryostat. Inside that is the crystal, and this is the crystal in the microscope. There's the microscope, and that's a picture of it in the screen. So we can see what's happening with the crystal, and behind there's an optical bench. I don't know if you can see that, the breadboard there, and the light, well, actually we use kind of LEDs really rather than lasers these days, but there's an LED light sort of being passed through under there and up through the bottom of that microscope, so we can shine light on it, and then we have to be careful because of course there's light coming down from the optical microscope as well. And then there's also spectroscopy off the side and the left that we're running together with the optical microscopy. So it's concerted single crystal, low temperature, optical absorption spectroscopy and microscopy all in one go. And you'll see hopefully why that's important as we go along. So that's the case of the experiments. And just to give you an idea of what's happening. And now let's look at some examples in terms of some results that we see in more detail. So before I go to actuators, I just want to give you one full example of the switching side of things. So light-induced molecular switching, because it's maybe a bit easier to understand and more common. So I already showed you one very quick example just for illustration of one of these molecular switches where in that case it was the chlorine. So now I've changed this here, so instead of chlorine it's methyl group, so this is a picoline basically, so 3 methyl pyridine. and that's now the transligand to this photoactive sulfur dioxide group. And there's a tosylate, the counter ions, just like the case before. Okay, and so in terms of what happens when you fire light at these systems, well, first of all, this is the dark state. Again, this is the crystallographic asymmetry unit. So it's nice and regular, nice and ordered. There's your 3-methyl pyridine, the transligand to the sulfur dioxide, which looks very ordered. And then what happens is when you fire light at green light at the crystal, you collect the structure again. You see now it's really quite disordered in its state, and that's because you've got a dark state, and on top of the dark state you've got this oxygen-bound sulfur dioxide ligand formation, and you can see the ADPs of the tosylate group, at least the SO3 part of that anion, are also quite significant as well, right? So they're nice and ordered here, now they're not. That's probably because there's some steric effect going on. And this is the packing diagram. I just highlight the arene rings here because, as you saw in the cartoon earlier, because these things get to really very close around this reaction cavity, that's a lot closer than maybe it shows by eye, then the arene ring of the tosylate often rotates to alleviate that strain. But not all of them have to rotate, it seems, and we learn this empirically. Right? This is not something that we have yet been able to properly model. But this is really us learning from real experimental data as we go forward. And so one of the things, of course, that has attracted our attention is exactly what is the mechanism behind this light induction process structurally. And so I've hinted at that as I've shown you in the introductory cartoon of what's happening. But this is really, I guess, our experiment where we tried to really prove what was happening in terms of the mechanism. And every case is slightly different, but this is a general trend that we see as a representative example. So we did this on this case, that the 3-methyl pyridine with the transligand. So this is now I'm going to show you a collation of many different full crystal structure determinations, right? So it's all on the same crystal, but basically I collect the crystal, for example, in the dark state at time equals 0, right? So you've already seen that on the previous slide. That's your asymmetry unit. And then what I do is I do a series of repeat experiments where I apply the light first of all for 5 seconds, and after 5 seconds I switch off the light. I keep everything cold. The same crystal stays on the diffractometer all the time, and then I collect a full crystal structure, right, with just 5 seconds of light on it, having switched it off. And then after you can see then there's a small change after 5 seconds. This ADP is there's a tiny change there. It's barely visible, but you can actually just refine the starting point of a sulfur here, right, which makes sense because it's the heaviest element in the sulfur dioxide part. But you can't actually see the oxygens of this photoisomer yet forming. And that's mostly all you can see with 5 seconds of light on it. And then what we do, having collected the full structure, again keeping everything cold, we then fire more light until a total of 10 seconds, and then collect another full crystal structure, data acquisition again, and then we collect the structure again. So we're basically building up a movie, right? So as more and more light is applied, we collect a snapshot crystal structure each time. And so now after 10 seconds, double the amount of light, we can now actually refine some small amount of population of our photoisomer there in the sulfur on top of the dark state. And actually this is now the first time after 10 seconds of light you can actually start to refine more or less the rotation of the arene ring that to alleviate the strain. And that makes sense, right? Because the more of this oxygen bound sulfur that forms, the more the strain builds up. So you're starting to really see it now. And then the time moves on, you know, 10 more seconds of light, you collect again, and you can start to really refine these structures now, because the structural information is so much more intense. And then 10 more seconds, you know, 10 more seconds, up to 60 seconds of light, and then that's now 2 minutes of light, right? And this graph here is essentially showing you, having refined each of those individual structures at each of those time points, what's happening to the photo conversion level of your different components that are changing in response to light. So the dark state in blue, that's really decreasing in population, which you'd expect from 100%, because you're seeing the formation of these photoisomers. All right, so so you can see that goes down to, in this case, about 80%. So in other words, 20% photo conversion, and then it makes sense. Then there's a symmetry involved in this, of course. So if you lose 20% of the dark state, you gain essentially 20% of the light-induced states in total, which actually seem to be split in this case between 2 different photoisomers, the side-bound and the oxygen-bound photoisomer, and then the sort of purple color, I guess, with the triangles, that's actually the arene ring, what we call the rotor. So that's growing in its population to help alleviate the strain caused by particularly the oxygen-bound sulfur in this formation. So that's kind of starting to show you really sort of the order of events, if you see what I mean, in terms of a sort of mechanism. And then what we did, we did this even further, and I'm just going to take that off the pointer, I think, because I want to press a button. I'm going to now show a movie. Hopefully you can see the movie. If not, please somebody shout out at me. So this is now us over a longer period of time, over 2 hours. And what you're seeing is, I'll play it twice maybe, the structures. Well, it's evolving in terms of the more photoisomer state is forming, and each of these clips, as you can see then go through, is another crystal structure determination. So a whole crystal structure data collection at each jump. I think I'll play it again just so we can now talk it through a bit more in detail. And on the top right, you're seeing actually the optical absorption spectroscopy change in step with the crystallography change, right? So, and then on the bottom left is what you've already seen. This is the indication of the photoconversion level changes, which are kind of more obvious, I suppose. Just so I'll play it one more time. So have a look at the optical absorption, right? It goes up really quick, right, after a few minutes, and there's even this peak almost that forms. Something saturating there, and then actually it comes over the edge of that and then starts to decrease, and you actually see the optical absorption at the sort of redder side increase, right? And then after a while it settles, and actually then it sort of, it sort of sides away. And so, having got all that information, now we've got this correlated information between optical absorption spectroscopy and crystallography, really seeing every single structure at each instant. We sought to see if we could actually put a mechanism on that. And we tried to then classify it into sort of steps, if you like. So, you know, this part, you know, there's clearly from optical absorption spectroscopy a rise in absorption at, you know, let's say 660, I guess, nanometers. And then you've got this rise in this kind of almost saturated peak formation. And these circles I drew just to give you an idea of how this correlates to the photoconversion level from the structural side, right? So this is the photoconversion level we've seen in the previous slides. So really quite quickly in this case, we're already at this. So we've already risen in optical absorption and sort of had some solvatochromic shift, if you like, to this point within a very, very short period of time, right? And that basically correlates with essentially the rise in the rotor. That's the arene ring that's converting. And you see the corresponding, you see a real drop in the dark state. Again, you'd expect that. So the SO switching is really quite fast, by the way. And then the oxygen-bound sulfur dioxide has grown really quickly, and is pretty much not quite peaked, but it's certainly peaked here at the sort of pink value here. So you're right at the top of this saturation here, right? So that basically seems to correspond with the peak in oxygen-bound sulfur dioxide formation at that point. So we do this empirically, right? We're obviously trying to map the structural changes, particularly looking at the maxima peaks and so on with the optical absorption features, and it does seem to correspond quite well in terms of then being able to build up a sequence and a mechanism that goes with it. And I won't go through all the detail here, but I guess I also just want to show you here before seeing the next slide that the mean square displacement amplitude for C6 is the methyl group, right? You remember the transligand is the 3-methyl pyridine group. So the methyl, the C6, is actually starting to wobble quite a lot after the orange circle, right? So if you look over here, there's your orange circle, and then there's, the optical absorption depletes at the bluer end, and red increases. So we'll have a look at what's actually happening there on the next slide. So trying to put that all together, we try to essentially make a sort of a mechanism, right, that relates the structure and the optical absorption properties. Really just taking those empirical findings, and so obviously this is our dark state, and this is our sulfur bound. This is what the single crystal optical absorption sort of characteristic looks like, and then we apply light, and initially it's first order kinetics dominated by the oxygen bound photoisomerism, with the A-beam ring rotating just like you've seen in the previous slides. And there are some close contacts. That's what we expect from this, this ring rotation to alleviate the steric strain. So all of that is fairly sort of modelable, first order kinetics up to about 10 seconds. Then it gets a little bit more complicated. It's still first order, but the rate constants are really, some sort of converged in terms of the rotor formation, the oxygen-bound sulfur dioxide, and also the U11, that's of the methyl group, have increased. And you see this hypsochromic shift, right? And we given what's in the literature from other ruthenium-based coordination complexes, not so much with single crystals, but nonetheless we assign these changes optically to changes in metal-centered charge transfer and metal ligand charge transfer. And then, it then gets a bit more complicated, and with these peak forming that you saw in the previous slide. So we can't accept that that's really first order anymore, and really correlated effects are definitely taking apart, and they're probably at the moment, for us at least, too complex to model, but we can certainly observe them and get their mechanism by using the experimental data. And you saw, as I showed you, C6, this is the methyl group, and at this point actually it really, this is wobbling like crazy. And that seems to be associated with this this change in the optical absorption here, and then it sort of equilibrates and sort of calms down, if you will. But the time we sort of looked at these time points, right? So there's a time point here. So that's up to a few seconds, and then a minute, and then sorry, this is annoying. Then 1 minute to 5 minutes, then 5 minutes to 10 minutes. I'm going to point out 10 minutes and 11 minutes, right? There's a change between 10 and 11 minutes in particular that we needed to understand a bit more. And then at 26 minutes, right? So, and again, what I'm going to show you is really what we've looked at. I found these things empirically, right? But something, there's definite shift in something structurally between 10 minutes and 11 minutes and at 26 minutes. So to try and really understand this, I actually plotted every single bond length as a function of time. This is like devil in the detail type problem, and look for differences, right? This is really sort of straightforward stuff, and this is what you see, right? So in terms of the ruthenium immediate surroundings, right? So this is your ruthenium environment. The coordination, it does what you expect in some ways. Bonds goes down as others go up, and that makes sense because you're getting this metal ligand charge transfer. But there's this kind of strange jump at 11 minutes, right? You saw 11 minutes that was a change in that mechanism I've just shown you. So something strange happens between 10 and 11 minutes, and also there's a bit of a jump at 26 minutes. And if you look at the ruthenium oxygen bond, so that's the oxygen 1A, that's the oxygen of the oxygen-bound sulfur dioxide group, right? It's the oxygen that's coordinating to the ruthenium. There's a really big jump at 26 minutes, right? So something strange is happening with the oxygen-bound sulfur dioxide photoisomer at 26 minutes, which we'll come to in a second. And at 11 minutes, this happens here. So this is the carbon 13 to carbon 14 distance, really shoots down, right? And actually carbon 10 to 15 it does as well. And that's actually in the this area here, right? So this is the arene that's rotating to alleviate the strain. So something strange is happening at 10 to 11, something to do with the arene, and something is happening at the 26 minutes, and that's something to do with the oxygen-bound photoisomer. So let's have a look at what we see. And after a long time, I looked at all sorts of differences, and at the 11-minute mark, between 11 and 12, this is what I guess I found, and it's pretty subtle. These are I'm showing you Hirschfeld surfaces, right? So these are the Hirschfeld surfaces, and I've circled this area here because it's it's a super subtle, and I'm just going to flick between 11 minutes, right? This is 11 minutes here, and I'm going to flick to the exact slide as an overlay of what you see at 12 minutes, right? And you just got to look at the bit in the circle, right? So did you see it? So it's I'm going to go backwards, right? I'm going to go back to 11, right? I'm just going to backwards a few, and all you can see, you see that methyl group. That's the methyl group from on the substitution onto the pyridine ring, right? So that's pretty much right on top of the arene ring. Can you see that they've got that steric disorder underneath it, right? And this is 11 minutes, and you see 12 minutes. Yeah, you see the red just changes, and there's a little rotation of the methyl group, it seems, as well. But I think really it's the bonding of the arene ring which you do see. And if I go back here quickly, you'll see that this is this drop, it seems, here. That's all I can see. I've literally looked at every single bond length and that interaction, and that's what you see. So there's some sort of very subtle interaction there that is definitely the only seemingly thing changing, but it's consistent with those bond lengths. So that's what happens between 11 and 12, and you can see how subtle these things are, and it's all because of this very, very tight reaction cavity, right, in the electrostatics behind that, very subtle. Just to make emphasize the point, I suppose. So we then see this strange thing at 26 minutes, which we know is something to do with the oxygen-bound sulfur dioxide that's formed as a photoisomer. And again, remembering all this is happening in the single crystal state, the only thing you see is changing differently, aside from that distance here, this bond distance from the coordination with the oxygen to the ruthenium, is together with the oxygen of the ruthenium, you see that the hydrogen of one of the arenes, again, that's the one that's moving to alleviate the steric strain. That's the oxygen, and then the sulfur, right? So in that reaction cavity, it seems that at 26 minutes, right, there's 26 minutes, these interactions, these with hydrogen, non-bonded interactions, essentially, they decrease as you would expect, as a function of time, and then suddenly they flatline. It's like they can't change anymore. They're somehow locked in some way, and these are consistent, very subtle changes, but they're very consistent. If we've done the experiment. Well, I've done the experiment again, and essentially you get the same manifestation. So I guess I hope that's helpful. It's really a very detailed example, but I think it to some extent illustrates just how complicated everything is, and how subtle these changes are with this, you know, the sulfide dioxide and this, and the arrangement and interactions it has with the counter ions and the next asymmetry unit and with the other ongoing ions as well. So so that's single crystal optical molecular switching. So now I'm going to extend that to single crystal optical actuation, and really it's everything I've talked about before by this point, but when we have the light-induced molecular switching, in the cases I've shown you, they're just molecular switches. But what I'm now going to show you is some more examples in this same series of complexes that not only undergo light-induced molecular switching, but as a response, if you like, to the sort of to alleviate the strain, if you will, instead of maybe an A-beam ring rotating to alleviate the strain, sometimes there isn't that option, and there are more catastrophic effects that happen. And so instead of just being a molecular change in response to the molecular switch, you actually get a macroscopic motion, right? And you literally see the crystal physically change. You know, you can see this just looking at the crystal through the microscope. Let's have a look at some examples. I've just got 2 examples I want to show you, if we can get through in the time available. So so the first one is, again, it's the same complex, except that in this case, so we previously had a 3-methylpyridine. This is now a 3-phenylpyridine, right? So it's quite a big ligand now, a substituent hanging off the pyridine. But everything else is the same. Oh, and instead of tosylate, it's chloride on here as well. And what happens, I'll tell you before I show you, what happens is we fire the same sort of green light at the single crystal. We keep it cool, same temperature, 100 Kelvin. And what happens is the crystal literally peels up. And I really mean macroscopically. You can see this in an optical microscope. It's literally the crystal itself peeling. We thought it was just going to explode or something, but it does something even more strange than that, as I'll show you. So before I show you the actual example, this is the crystallography, right? So this is the dark state, nice and ordered, as it always is before we apply light to it. And then we apply light at 100 Kelvin, green light, and, you know, suddenly all of these ADPs are much bigger. And this is this kind of modeling disorder, but it's, in this case, a side. So what's that sidebar? Well, there's your dark state, and it's sort of being displaced by this oxygen bound sort of configuration here, right? So that's just showing you the crystallography of the light and dark induced species. But let's actually now have a look at the optical microscopy that you see, and I'll show you. First of all, this is an experiment where this is the optical microscopy, right? And we're applying light. We do that for 2 hours. Obviously, I've sped that up. And then, having applied lights, can you see what happens? I don't know if that's obvious, but literally the light cut essentially a sort of hole, if you like, or a stripe, and then the crystal peeled up, just like you peel up a potato. And now we warm it up, and the color changes back to its original color. And can you see the peeling comes down? It's like a bridge maybe that closes down again. And you think it's going to be damaged, but actually the crystal largely recovers, right? I don't know how obvious that was. I'll play it again. Hopefully we've got time to do that. So let's have a look at it again, just so it's more familiar in terms of what you see. So there's the crystal. We're applying light at it below the right temperature. And then here it goes about now. There, you see the color changed, and literally the whole face of that crystal comes up. It's like it is peeling up, like a sort of drawbridge, right? And it's really, it's almost like that. When I was doing the experiment, you could see it really like this. You thought it was just going to flip off, and it actually then comes all the way back down, right? So imagine the forces that are involved in this, the molecular scale, and then it pretty much recovers, right? It's almost like the crystal is going to fall apart, but it actually, you see it's now becoming transparent again. It's changed back to the original color. And actually, having done that experiment, don't want to run that again. I did it again. This is now cycle 2, right? So I thought the crystal may have died. So I thought, let me try that again. So I repeated the whole process. And you see it, you know, I'm probably hurting the crystal a bit by now, but it still comes back to its state. And actually, in this case, it joins up that cut, right? Actually, really, it's like it's got some memory or something. It's really strange. Anyway, that's what you see. As you can see, you literally can see that very big macroscopic motion. And, you know, these are just still pictures, right? So you see the cut and then the light induced, it's starting to peel up, and then it's getting darker and darker, and it's really peeled up here. And then you put the heat on it and warm it up, and then it goes back to its original configuration. And it's repeatable. So we even did, we put in some optical absorption microscopy, and we kind of, you can highlight, you basically you have a 2-dimensional grid in terms of the optical absorption spectroscopy. So what you can do is actually find the pixels on the crystal for each different optical absorption part, if that makes some sense. So I could get the optical absorption of the point in the white circle there, which is where you get that cut. You see the next slide B, where the white circle now is literally inside the bit that's cut. So that's in some form a sort of a shallower part of the crystal, right? Because part of the crystal's opened up. So you should get less absorption, and you do. In fact, you at that very point, your optical absorption spectra you can actually get is much more corresponding to the light-induced state without the saturation that we're getting on the left. Right, you see that peak is much more saturated, and that's because you're going through a thicker crystal, right? And you've got all this sort of effect of the peeling on top of it. In terms of the crystal lattice, the beta value is quite significant in its change between dark and light state. So from sort of 77.9 to 99.9, that's quite a big change. And again, we tried to come up with a mechanism to, you know, explain what was going on. The crystal, by the way, is actually a 50% pseudomerihedral twin, and that's probably quite important in terms of the mechanism. So we think, so this is our photoisomerization. Remember, it's 50% twin, so that's it, plus and minus in the B direction, right? So that's quite important. And that the twinning therefore gives it the option to be, you know, some arrows this way and some arrows that way. And then as light keeps building on, you get this crystal strain effect. And of course, that's manifested in, you know, this peeling effect, and these are the sort of various forces that you would expect to be on it. And so it seems that the crystal, as far as, you know, I can kind of work it out, it seems to buckle, and because you've got the domains from the twinning, that's okay, and it's consistent with beta, because that's the beta which is the biggest change, right? And then, you know, having buckled, and then you keep applying light, and then it sort of actually eventually would, I guess, peel, right? I mean, it's a sort of cartoon, right? But it's our best understanding of what's happening at this stage. So that's that example. So that's an example of macroscopic peeling, or so optical actuation. And then I just want to show you the final example if I've got time. I'm not sure what time I started, so please somebody sort of yell at me if you want me to stop, but I'm just going to otherwise do my second example. And this is quite recently published, just last year. And this time it's going to be a much more strained example. The same family of compounds, but instead of, and I've still got this pyridine ring on it, but instead of the 3 substitution, I've now got a 4 substitution, and it's a bromine. Okay, so that's really the only difference in terms of the chemistry, and I've still got back to my normal tosylate groups as the anions, right? In this case, for the first ever time in this series, so this is the dark state at 100 Kelvin, but I managed to capture both the light-induced species of the oxygen-bound photoisomer in 100% state. This is, you know, it's really hard to get these, you know, fully clean to get the right temperature and the right light, 100%. So it's not disordered, right? There's no dark state left. 100% conversion in the oxygen-bound form. And also, and I did this, and I actually got this by accident because I called it down to 90 Kelvin because that's the lowest that the cryostat will go in my case. And I got this, and then I saw some color changing, which was unusual. And actually, it turns out that I had only just got it because if you warm it up to 100 Kelvin, 10 degrees above that, it loses the oxygen-bound state entirely, and it goes to the side-bound photoisomer. And again, what's great about it is it goes to the side-bound isomer 100%, right? So there's still no dark state. So this is the first ever time I've had it so that you can get, you could isolate the dark state, the light state in both of the photo-induced configurations. That could be potentially useful. It's so clean optically from a sort of photonic perspective. That's sort of a 0, 1, and a 2, right? So that's quite cool. It's also very clean in terms of the optical spectroscopy because we've always had an insight into what, which part of the optical absorption belongs, if you like, to which photoisomer and the dark state, but this is really clean, so we can literally say that this is definitely the optical absorption characteristics of the dark state and this isomer and that isomer. So that's quite helpful. But look at the changes in the crystal unit cell parameters, right? So this is the dark state, and then this is the light state, and you see that difference? That's like a whole Armstrong difference, right? That's huge, right? And you'll probably not be surprised to know then that the crystal fractures in what feels like a horrible way, and you're looking at this doing the experiment and you're thinking you're about to lose your crystal and having to start the experiment all again, but you don't actually have to do that. This is what happens. So this is the dark state. This is the glue, by the way. Well, it's the oil frozen, and then it's photochromic, and you see all these stripes. These are the striations. You see how strange that is. And then that's the light state at 90 Kelvin. Then you go up to 100 Kelvin, and actually I heated up even a bit more, and I sort of keep heating up until it gets back to room temperature, and it's pretty much recovered. It didn't quite survive. Actually, that was already there, so that's okay. So it's not perfect, but it's sort of recovered. And these holes, these are you can physically see those right under an optical microscope, but they actually they come back together again. You see that? That's literally cracked, like visible kind of gap, and it recovers like that, which is kind of cool. And so we then thought, well, let's look at the actual. Let's zoom in and look at the actual microscopic strain, at a point in this crystal. So if this is the scale of on the optical microscope, we then thought, well, let's do an atomic force microscopy experiment in the way that we would never normally do an atomic force microscopy experiment, just so you know. So we're going to actually do an atomic force microscopy experiment now where we look at a 4x8 micron area, right? So we're going to look at almost that sort of square on the left of that crystal, right? And so the reason we want to do that is to see if we can actually sort of track this sort of these striations forming spatially, and it turns out you can. And I spent a month in an AFM room doing this, by the way, so I pretty much didn't see the light of day. Anyway, so what you're going to see now is you're going to see. I'm going to put the light on. Everything now is an AFM experiment, so atomic force microscopy. I'm going to shine light at it. At actually less than 100 Kelvin in this case. It took us a lot more time because we had to get the light in very glancing angle, but so that's why the times look extended. But let's see what happens. So we can run this. There we go. So it's hopefully running. You can hopefully see some changes, and the darker color means more depth, if you like, right? Okay, so that was a very quick all the way through. And I don't know if you can see what's formed. I may run it again. You see these two channels, these dark kind of vertical things. Yeah, they're actual channels in that crystal where it was all the striations. They're the striations in a very just part of them. I'll just run it quickly again. So, if it's going to let me run it. Yeah, well, there we go. So pretty much random. And then it actually forms these kind of V shapes. It's very subtle now. You see those, they're forming. And there it is, right? So you're right in, there's two striations there. And then what happens, I managed to keep it just about steady to do this. And then I heated it up. Oh, I'm running again, sorry. Oops, hang on, go, oh no. Oh, there it is, yep. So now we're cool. And I'm just under the temperature of the metastable state, right? So I'm warming up now. And you can just see that they're the double channels that you see, right? And I'm going to heat it up now. Oh, sorry. Go on. There we go. Right, you see that channel? Collapse. Boom. So that's, and then then I lose it a little bit, right? Because it's moving around a bit. When you heat it up, it's hard to keep the space. I'll play it one more time if that makes some sense. But anyway, the key thing is, this is really us looking right at the optical, right into that striation and seeing it really does, come and go with the light and the temperature. Anyway, it was a fun experiment. So, but I think ultimately, what we'd like to do is really go back to do this experiment again. And I'd like to look at the forces and actually quantify things, which would be really super neat. Anyway, so that's the actual instrument for the atomic pulse microscopy. And it's quite a beast. This was me trying to put light in it. It took us forever to get this right, but after 3 times, I think we managed it. So that just to show you what it looks like. So I guess that's really everything. We're a long way from putting this into a quantum sensing application, but I guess over the years, I've looked at a number of these family of materials, and I'd say we're trying to monitor these sorts of properties. The thermal stability, I'm still down at, if I'm lucky, 150 and that's the sidebound form, and mostly I'm still at 100 Kelvin. Be really great with room temperature ones, and then photo conversion, optical control, I'm still working on. I probably got to about there on a good day, but that's where we're at. So thank you to everybody that's involved. And really thank you for listening. Hopefully it's not too long. Sorry, it's now 5 o'clock. Oh, sorry, 6 o'clock in your world. That's it.
Thank you, Jackie, for a very interesting lecture and beautiful videos. Now we are open for questions, and we already have questions. Let me just read it. Yeah. The first question from Jarosław Majewski. How fast, on a single molecular level, the optical switching occurs? These are the femtoseconds, picoseconds time.
So do you mean the formation
single
of
molecule,
the soft clouds?
Yeah. How fast the single molecule?
Yeah. So if you mean the the population build-up's quite slow, as you saw. I mean, it's a sort of seconds, but to the very first one to switch, we can't capture. It's too fast. So we always see something, and in the optical microscopy, it's already switched before we can capture it. So I mean, based on other studies, but I'm sort of guessing. I mean, it's like picosecond, maybe it could even be faster. But yeah, well, I can't capture it. I've tried transient absorption spectroscopy, and we still can't catch it at that speed, actually. So I mean, that is hard. It's hard to do transient absorption spectroscopy though on single crystals, for reasons that are I guess obvious, which doesn't help. But yeah, we can't catch it. It's super fast. Yeah.
Your experiment, I mean, to reach the stationary point of the maximum percentage of the switched version of the molecules, it's quite long. Is it reversible, or once the molecules are switched, they stay like that?
As far as we know, as long as we keep it cool, and when I say cool, I mean 100 Kelvin or so, then as long as it stays at that temperature for all the time we've studied them, you know, it's stationary, right? In terms of once you've got all the light populating as much as it will populate, it will stay populated. I've not, you know, I guess what's the longest I've left these things? I've certainly done experiments that last several weeks, right? And they're still, you know, I don't have any problem as long as I keep the everything at 100 Kelvin. For practical reasons, I can't keep them for so much longer just because I get told off for using too much cryogens. But yeah, I mean, they do seem to be really metastable. But of course, the moment I warm up, it goes back to the dark state. Yeah, yeah.
And when you crystallize the crystals, do you need to crystallize them in dark, or it's in normal condition?
Yeah, so the crystals actually form straight out of the reaction pot, right? So and the last stage is a cooling down stage. So basically, partly because I want to keep I want to slow the heating down slowly, so that they form maybe nicer and bigger crystals. Partly I put essentially silver foil around it, or aluminium foil really, and that also, of course, helps to keep the dark away from anything. So as far as you can, I try and do these experiments in the dark. Yeah, yeah.
Mm-hmm. Krzysztof?
Jackie, could you be a little bit more specific about details of X-ray data collection? I'm very much interested in how did you collect X-ray data?
Sure, yeah. So there were two types that I showed in the presentation. One was actually on a laboratory machine. It was what was it? Let me think. I think it was a Bruker. Sorry, I've used so many different diffractometers over my time, but I think, yeah, it was anyway, it was a classic lab-based CCD detector diffractometer. And I can actually now do a lot on the laboratory diffractometers. Obviously, you've got to collect for longer, but that's fine as long as the crystal is big enough to do that experiment. However, if you want to do some of those time-based experiments that I showed you, even though I can do those on a lab-based spectrometer, it would take me too long to justify using the diffractometer for that long length of time. So I would do those experiments at a synchrotron. The other reason to do those experiments at a synchrotron is also because you can, you know, if you keep firing light at these crystals, sometimes they do die because, you know, particularly if you're doing repeat experiments. So it's in some ways less temperamental to do it at a synchrotron, because you can also get away with smaller crystals. And so, you know, the light is somewhat less problematic, right? The smaller the crystal, the more optical light you can get through, right? So the less likely they are to, you know, explode. I haven't shown you examples of exploding crystals. That's because I never have any, right? Because I can show you the picture of an empty pin. So yeah, so that I don't know if that gives you enough detail, Christoph, but it's you know, it's at that level. But really, the each of those time points was a whole data collection. You know, in the same way that you would do a regular you know, data collection in terms of the numbers of, you know, reflections you would collect for a given space group and all of these things. Yeah.
In those data collections, do you have a chance to get, say, high resolution data sets, or are you getting them or not? How it is?
Yeah, so I have tried. I guess I'm not sure I would get charge density level, but I've got some fairly good quality data up to. I'd have to check, Christoph, in terms of the actual resolution, but I've certainly tried to get as high resolution as I can. I've even tried to do a charge density experiment. And I got stuck with the absorption of the ruthenium, right? So I had enough data to get through the whole kind of Q10 thing, except that I got totally stuck with the ruthenium because it you know, there's just a massive blob of residual electron density around the ruthenium. So that's where I ended up. I even tried an anomalous X-ray diffraction experiment to try and then get the difference, to take away the ruthenium effect by some difference, and that didn't end well either. So, but yeah, I would love to do it, but so far not yet.
Did you have a chance to collect data at free electron lasers? I mean, just to catch this first moments, this picosecond, femtoseconds, or?
Yeah, so I haven't done that yet. I've certainly had conversations with people about it, but yeah, I guess just a matter of time. I guess I haven't quite got there yet. But yeah, I would love to do that type of experiment to really capture that first part. Yeah.
Just for your information, there are also compact free electron lasers being built all in a few places around the world. So they are not that expensive as a European free electron laser at DESY. Probably you could have this kind of equipment in your institute.
That would be nice. So, but yeah, so I guess there's a starting experiment to be done first, proof of principle. But yeah, I would love to do that experiment to really understand all that timing and the exact mechanism and the movie, if you like, of what happens.
Yeah. You trace changes of structural changes, but it would be great to trace electron density changes. How do they change, variate? Okay, thank you very much.
And just to follow up on that, Christoph, you can see with the optical absorption spectroscopy that I was showing, I can definitely see through that indirect evidence that you're seeing these metal ligand charge transfer and the metal centered charge transfer. So you would definitely see that if you could actually get that high resolution electron density map, you'd see that happening right through.
Yeah, but you could find quantitative, say, relations between changes in the spectra and changes of electron density. Would be great, really.
Yeah, it would be an amazing experiment if we could do it. Yeah.
A question from Kristina Smokrovich. Did you try making an analog with NO2 instead of SO2, so nitrogen?
So I think a long time ago, I tried a number of different things. Nothing worked very well. I can't remember if I tried NO2. I tried SCN. I tried, I think NO, because, with the triple bonding as well. And then, yeah, I think I did, and it didn't work so well. So I carried on with sulfur dioxide, but don't let that put you off. It might have been just that we're not so good at the chemistry synthesis or something. I'm not sure. Yeah, I mean, I think what's the most important thing is that that you keep everything as an ionic crystal, right? Because if you start to try and do this on neutral systems, it doesn't, you can't get the result. I've just noticed this with many other papers. There are other, there's not so many, but in other systems, if you look at photocrystalography examples, then apart from the cycloaddition type things that are really reactions, in terms of really kind of photo ligand photoisomers, I'm not sure I know anything that isn't an ionic crystal, right? And there's probably a reason for that. So I think that's the most important thing. I think the sulfur dioxides work really well because the sulfur is so soft, right? So you've got your sort of Lewis acidity is very, very labile, right? So from turning to a sulfur bound to oxygen bound is a really nice kind of easy switch. Yeah.
Anya Kravchuk?
Well, I see a lot of questions in the chat, but I guess I have priority. I will try to be quick. I wonder about the orientation of the crystal. So does it matter actually for your studies, especially if you have this kind of a peeling effect? Do you think that if you, let's say, change the orientation of the crystal, you would observe the same effect, or it doesn't matter really?
Yeah, so it's a great question. I'm certain that it will have an effect, right? The different, the direction of the light you apply onto that crystal face. In terms of practicalities, the only way at the moment I've kind of got things to work is when I apply it. So if the light, these are all very plate-like crystals usually, and I apply it on, so the light is normal to the big face, right? That's partly so I can get a light bathing the whole crystal in a nice uniform way, but partly also because I haven't got to go through so much thickness, right? Because if it's too thick, you're just not going to get the light through, and then nothing will happen, right? At least nothing useful. And so, if I turn the crystal like this and try to put it down the thick axis, nothing will happen. And I think, with the example on the peeling example I showed you, at least as our best guess as the mechanism, right? Because it's twinned, you've got these domains that allows you kind of the light coming this way, and then the twinning is actually along that way, so you can have domains so that it can buckle out of the plane. Otherwise, I don't think that would happen. And then the striations form, and then they come back. But again, I've sort of looked at, the sort of the different faces and what's happening at each face as I look at the mechanism. That's more to try and explain it, I suppose, a sort of rationalization exercise after the experiment. But yeah, it's more a practical thing. It's also in terms of the optical microscopy. Physically, I've got to have the crystal. It's actually upside down. I don't know if it's obvious from that microscopy setup I showed you. You've got the cryostat, and the cryostat is essentially it's an inverted microscope. So it means you have to put the cryostat upside down, so the crystal's hanging in the sort of perfluoroether glue, oil that we use, right? So it's just viscosity that's holding it upside down, and then of course we have to then cool it quickly to freeze it. And then just hope it doesn't fall off, and because sometimes when you fire light, that's going to cause a heating effect as well, right? So these experiments, I'm showing you the ones that worked. I could give you about 10 hours more on crystals that don't work, right? So yeah, it's tricky, I think, is the answer.
We have a thank you very much for your very interesting lecture from Elżbieta Bartoszek-Adamska.
Okay, thank you. Hopefully it's helpful.
And from Uli Englert, thank you for presentation. Is the degree of photoconversion exclusively a function of chemical system and the solid state structure, or do real space aspects such as moisicity or even crystal size have a measurable influence?
Yeah. I would say the crystal shape and size will have an influence. And it comes a bit to the question that I think Hannah just asked me, actually, in a way, right? What happens if you do something a different orientation? Also, what happens is the different thickness, right? And it's just a matter of time. These are so hard experiments in the first place that, if I had 100 crystals, I would do 100 experiments, right, to see what's the effect of shape and size. But we're still at the beginning, really. I mean, so, and this has already been, I don't know, on and off 15 or something years of work, possibly longer if I want to think about it. So it's for sure that's going to be an impact. And when you see these macroscopic effects, right? I mean, we've got the peeling, and I've got that working, and I've tried long crystals. I've tried, the crystal I showed you, and you see the same effect, but the manifestations may be just slightly different. If they're very long and thin, for example, they're much more likely to break, like properly break, and never, as in like fly off, like the top just cuts off and falls to the other side of the cryostat, for example. Yeah.
A question from Shabam Sam. In the photo-induced crystals, is there any change in the reflection pattern observed by a single crystal X-ray diffraction during photoconversion? Any change in the any change in the reflection pattern? I mean the diffraction pattern.
Oh, okay. If you mean, do we see any diffuse scattering? Sometimes is the answer. Yes, we do. Of course, these look like disorder systems, right? And depending on what we see, certainly if we see some of these real kind of fractured, striated things, we see massive, things happening, right? So, you'll see really long stripes, and sometimes you see the full, two-dimensional crossing, kind of when there's a plane forming. Yeah, a whole load of stuff sometimes, but sometimes it can be really subtle, and yet there's still huge amounts of disorder, right? And I guess there's enough people who understand disorder far better than I do to understand that there's proper theory behind all of that. But yeah, absolutely, you would definitely many of these systems see diffuse scattering.
But Jackie, do you take this diffuse scattering into account when you are interpreting the final results?
So that's a good question. I think I integrate them, so everything's done on a CCD, right? So I integrate them as best as I can to capture the information, but I'm definitely losing the tails, right, in the behind, and there may be some pollution, in terms of the intensity of neighboring ones if the streaks, go across. So I'm not explicitly modeling them, and I guess it's relevant to say that, the very fact that you're applying light to these systems means that your internal R agreement increases quite a lot, because the crystal's quite badly affected in a fairly macroscopic way as well. So I think it's quite hard to model diffuse scattering in the way that we understand it in crystallography, because what's also happening on top of normal diffuse scattering at the molecular scale is physical cracks in your crystal that may go away when you warm it up and not, if you see what I mean. So I think it's part of it's just beyond my level of diffuse scattering understanding, I suppose, but part of it's just worrying about much bigger problems in terms of the quality of the compromises when you apply light.
Thank you.
From Vitali Shapura, I'm very sorry if I pronounce your names wrong. How exactly absorption spectra of single crystals were measured? What are typical thicknesses of these crystals? Did you see isobestic points in absorption spectra of photoresponsive crystals with light exposure?
Okay. Wow. So there's potentially a whole lecture on that. I'll try not to do that to you. Hang on, let me just go back a few. In the past, I have seen some isospecific points, but mostly we just see these sorts of things, right? So we see a rise in the optical absorption spectra, and then there's often a solvatochromic effect, right? So, there's no solvent actually, so hypsochromic rather effect usually from sort of red pushing into the sort of green blue side, and then it collapses, and then sort of sometimes you get this red equilibration increase at the end. It's let's see if I've got anything else. I mean, that is the optical absorption spectroscopic apparatus right there. You say this is the optical cryostat. Your crystal's right in the middle there. This is a picture of the crystal up here, and the screen. You're looking right into that center point here, and then the microspheres, or the microscope's there, and to say the green light is coming through. It's a fiber coupled LED light. So it's decoherent, which is quite important, because it means that you can, instead of focusing too fine, you actually don't want to focus too fine with the light, because otherwise you don't bathe the whole crystal. What you do is have a pinpoint on the crystal, and then you just burn a hole through the crystal. You don't want to do that. So you want to have actually decoherent light come in, and that's why we use these fiber coupled LEDs. So they have actually a bandwidth. They're not, this one that I cite at 505 nanometers is the full width half max center point, right? But there's probably about 20 nanometer width on it with any degree of intensity. But they're also great because they're very flexible if you use these LED systems. So you can then just run them through, you know, optical fibers and into the back end of this microscope. And then, as I say, on the side of that, there's a spectrometer. All the details are in the paper, usually in the sporting information that I usually have to write up if it's of any interest. And is there anything else I can helpfully say? Just that they don't ever exist all of the time. This picture I've shown you is literally the equipment that I have to put together every time I go to Argonne usually, and I have to run around to find the cryostat, and I have to run around to find the microscopy, and I've usually got somebody helping me do that. Luckily, who knows Argonne a lot better than I do. So it's really a bricolage experiment. We have to make everything, and I go over for a month and I have to build it all over again, and then every time hopefully it gets easier. And obviously I've got a lot of help from the local staff at Argonne. They're really great, but yeah, it's a bespoke arrangement. There's no commercial machine. There's I don't know if there's ever going to be a demand for that, but that's what it looks like anyway.
And what's the typical thickness of crystal?
Oh, the thickness. So what was the exact question about the thickness? Does it matter? Or what is the typical? Sorry, the typical thickness. Well, that varies quite a lot. If I'm doing a synchrotron experiment, I might go down to, wow, even like if I'm lucky, I might get down to like, I don't know. What can you barely see these days? I feel it's like nanometers or something almost. It's probably not that, but it's like 5 microns or something. It's a silly small amount of thickness. And in the lab side, they can be up to. Well, I've done things. I've had to actually change the lab collimator on the X-ray reflectometer to like up to 0.5 millimeters. Right, so that's super thick in our world. So yeah, anything in between those two extremes, I guess, between let's say 5 microns and 0.5 millimeter thick. Yeah.
From Łukasz Golon, I may have missed that, but how confident are you in that metal group rotation in the time-resolved photo switch experiment? Is it easily visible from the electron density? Were these models based on the independent atom model or Hirschfeld atom refinement or something else? It would be interesting to see how well transferable spherical atom model works with these data sets.
Okay, so just to check, it was how confident am I that I see, was it the alien ring rotation? Is that
metal group rotation, the hydrogen atoms visible.
Methyl, yeah. So yeah, that's fair. So where I had so I've gone too far. There it is, yeah. So yeah, you're probably looking about that. So that's what the crystal structure looks like. It's idealized, right? It's an independent atom model, right? I think actually I was less worried about that and more interested about actually what happens in the center of the arene ring, right? You see, oops, sorry, that's the green, the red. You see, that's yeah, I don't know. I mean, it's an independent atom model refinement, right? So yeah, some of that's idealized for sure. But what's interesting is actually that it's not. It's a bit of a what's the word? A sort of optical illusion, because actually, if you look at the bond lengths, I wasn't showing you the hydrogen. I was showing you the carbons, right? That's the carbon on the arene ring. In fact, that's C1314, right? Which is one of the arene rings. So actually, I think it's really the arene ring that's the offender here. It's very easy on the eye to look at that, right? But that's odd. That the hydrogens there are idealized on the methyl, right? And so when I do these analysis on the methyl, I was focusing on the mean square displacement amplitude of the carbon, not worrying so much about the hydrogens. So that's why I'm confident, because I focused on the carbon on each of the interacting units, if that makes sense. But no, we haven't done any of these complicated things that was just described beyond independent atom.
They are not such complicated, but probably it would be worth to try. I guess all the data are available, right? Or you can easily share them.
Yeah.
Kevin Nick Bandibas, very nice and interesting talks. Thank you. I'm just curious. Have you considered using a more bulky stabilizing scaffold such as TP star? What that would be?
On which part of the compound? You mean on as the X, the transligand? Do we know?
Maybe like you mentioned that that it usually has to be an ionic system, but maybe it's not about having ionic system, but also about having this neutral or not interacting molecule, which is diluting the system or giving you space to do this photo isomerization. So maybe that's the related question. Have you tried to crystal with something which is bigger than the scatter ion?
Well, we have tried, but we've never been successful. We once tried to put these into MOFs, for example, and that didn't work.
Yeah.
So,
okay.
But the best way, and it's much simplistic, much more simple than any of that type of thing, that I've tried to get kind of steric stabilization. I've tried, for example, heavier counter ions, although that tends to make it worse because I'm just creating a reaction cavity that's even more complex. The other thing I can do to get some sort of stabilization in terms of the photoconversion, and again, it depends what you mean by stabilization, right? But I spent a long time trying to get the photoconversion up in this series, right? And I started to have a lot of success when I moved over to the 3 substituted pyridine systems, and methyl I've shown you. What I haven't shown you today is I've been through the whole halogen series of the 3 substituents, right? So I've got fluorine, I've got chlorine, I've got bromine, and I've got iodine. And sorry, just for time I didn't show them, but I've done the photocrystallography on all 4 of them. And what you find is the heavier the atom, right, it does stabilize. However, the fluorine only just, it's a very small photoconversion that I can get. I can't get anything more than, I can't remember the number, but it's really small, like 10% type level. I can't quite remember the number. But and then when I go to chlorine, so heavier, I get to I think something like 40% conversion, depending on how well I focus the light. And then when I go to bromine, when again heavier, I then get 100% for the first ever time. That was the first ever time I got 100% photoconversion. And then I got iodine to work, and again that's 100% photoconversion. But the problem with iodine is it's so the ADP is so massive. It's just I modeled it, and the only way I can model it eventually was actually as 2 sites. So it's just huge. It's just, I don't know if it's static or it's just, I think it's really just wobbling, to be honest, around in this big kind of cavity, and it's just so heavy, and it's heavier than anything else in that molecule, right? Iodine. So bromine sort of has got a fairly big ADP as well when you apply light to it, but yeah, so it sort of anchors, I suppose, it, but it has some detrimental effect in another way. But at least I can get 100% photoconversion. So yeah, it really depends what you mean by stability, but yeah, there's a whole load of options to work with there. Yeah.
From Razakia, nice talk. For your information, most of the works related to nickel nitrogen dioxygen complexes were done by Paul Raidby at Bath University with 100% reversibility. Quite exciting. And now Laureen Hatcher is doing at Cardiff University with laboratory-based diffractometers.
Yes. So yeah.
Yeah, and a very good research team at Warsaw University, that's Kasia Jarzemska, related to the photo-induced linkage isomers. That's all related to nitrogen and oxygen.
Yeah, okay, so that's absolutely fair, yes, and correct, right? So yeah, sorry, I didn't mention that, but it's obviously it's not my work. But yeah, no, I think that's a really good reference to comment on. Yeah.
Thank you from Łukasz Gołom, and thank you. Yes, confirmation from Kevin about this bigger cavities or molecules stabilizing the system. That's all from the chat.
Great. So, am I off the hook?
I think, yeah, it was a half an hour discussion. So thank you once again, Jackie.